what if there are questions, even in the seemingly objective world of mathematics, that simply cannot be answered by any logical process? It's a thought that, well, it can really challenge how we think about truth.
Indeed.
Mhm.
And we're not just talking about problems we haven't solved yet, the really tough ones.
Right.
We're actually talking about questions that are fundamentally unanswerable within certain specific mathematical systems.
Right.
It's a profound difference.
Yeah.
Suggests limits, maybe not just on us, but on logic itself.
Absolutely. So today we're diving deep into this fascinating realm of undecidable questions. Our mission is to explore what they are, how they shook the very foundations of math, and, well, the pretty wild ways mathematicians are trying to move forward now.
Yeah, from proving independence, which was huge, to this idea of a multiverse of mathematical truths.
A multiverse. And even maybe a new way to unify things again. We'll get there.
And as we explore this, you'll see how that search for certainty, for absolute answers in math, often leads to, well, deeper questions about knowledge itself.
What does it even mean for something to be true?
Exactly, or existent. This deep dive shows how mathematics, chasing precision, kind of stumbled into its own philosophy.
Okay, so get ready to stretch your mind. We'll start with undecidability basics, the halting problem.
A classic.
Then through Kurt Gödel, his huge discoveries, and the famous Continuum Hypothesis.
Ah, yes, CH.
From there, Paul Cohen's really revolutionary method called forcing.
Change everything.
And then we'll land on these bigger ideas, the multiverse, and maybe even a surprising new axiom that tries to bring order back.
Okay, let's unpack this. Undecidability. What does that actually mean in this context?
So at its core, a problem is undecidable. If there's just no algorithm, like no step-by-step procedure a computer could follow that can always give you the right yes-no answer.
For every single possible input.
For every possible input in a finite amount of time. And the key thing is, it's not about being super hard or taking ages to compute.
Right.
It's fundamentally impossible to solve algorithmically in all cases. It's like a built-in limit. A hard limit. Can you give us a concrete example, something to grout onto?
Absolutely. The halting problem in computer science is, well, perfect. Imagine you write a computer program.
Okay.
And you want to know, for any program and any input you give it, will it eventually stop halt? Or will it just run forever in some loop?
Yeah, that's a practical question.
It is. The halting problem asks, can we write one master program that can look at any other program and its input and tell us definitively, yes, it will halt, or no, it runs forever?
And the answer is?
The answer, proven by Alan Turing, is no. There is no such universal prediction algorithm. You can check some programs, sure, but no general method works for all of them.
Wow, so that's a real-world limit on computation. But you mentioned this takes us deeper into math itself. The Continuum Hypothesis, CH, how does that fit?
Ah, CH. That's where things get really fascinating and much more abstract. It's about the sizes of infinite sets.
Sizes of infinity.
Yeah, we know some infinities are bigger than others, right? Like the infinity of whole numbers, 1, 2, 3, is smaller than the infinity of all real numbers, all the points on a line, including fractions, irrationals like pi.
Okay, I think you can't pair them up one-to-one.
Exactly. The real numbers are a bigger infinity. So CH asks, is there any other size of infinity strictly between the size of the whole numbers and the size of the real numbers?
Is there an intermediate infinity?
That's the question. Or, to put it another way, assuming a standard rule called the axiom of choice, CH, says any infinite set of real numbers is either the small infinity size, like the whole numbers, countable, or the big infinity size, like all the reals. No in-between size is allowed. Seems simple, but it's not.
Just a question about infinity sizes, but this is where Kurt Gödel comes in, right? His work was pivotal here.
Oh, absolutely pivotal. Gödel's incompleteness theorems in the 1930s were, well, a bombshell for mathematics.
How so?
He showed that in any consistent mathematical system that's powerful enough to include basic arithmetic, like our standard set theory, ZFC.
ZFC, Zermelo-Frankel plus choice, the usual rule.
That's the one, the bedrock. Gödel proved that within any such system, there will always be statements that are true, but cannot be proven using the system's own rules.
Whoa. True, but unprovable.
Exactly. It shattered the dream of a complete perfect system where everything true could eventually be proven. And this directly pointed to things like CH possibly being undecidable within ZFC.
So ZFC, our best rule book, might just not be strong enough to decide CH either way. True or false?
Precisely. It couldn't be proven true or false from the ZFC axioms alone.
How did Gödel himself react to that? What did he do next?
With incredible insight, he developed something called the constructible universe, usually written as L. Think of it as a kind of minimalist, well-behaved inner model within ZFC.
An inner model.
Yeah, a specific collection of sets built up in a very precise way. And in this model, Gödel showed that the axiom of choice holds and the continuum hypothesis is true.
So he found a world consistent with ZFC where CH is true.
Exactly. That was huge. It proved that CH is consistent with ZFC. Meaning, if ZFC itself is logically sound, then adding CH as a new axiom won't suddenly create contradictions. It could be true.
But just because it could be true in one special model doesn't mean it has to be true in the broader sense, right? It feels like only half the story.
Absolutely right. It only showed consistency, not necessity. And this really kicked off what people call Gödel's program.
Which will?
To try and resolve these undecidable questions, like CH, by finding sort of natural or obvious extensions to ZFC. Usually by adding new axioms, often these large cardinal axioms.
Large cardinals, what are those?
They're axioms asserting the existence of incredibly, almost unimaginably large infinite sets. The hope was that these superpowered axioms would be strong enough to finally settle questions like CH one way or the other, to complete the picture.
Okay, so Gödel shows CH could be true within ZFC, but who showed it could also be false? That's the other shoe dropping, isn't it?
It absolutely is. And that was Paul Cohen in the 1960s. He developed a completely revolutionary technique called forcing.
Forcing. Sounds dramatic.
It kind of was. Cohen figured out a way to start with a standard model of ZFC and sort of force it to grow into a new, larger model, a new mathematical universe.
Okay.
And in some of these new universes he constructed, all the old ZFC axioms were still perfectly true, but, and here's the kicker, the continuum hypothesis was false.
Wow. So, wait.
No.
Gödel shows it can be true. Cohen shows it can be false, both within worlds that follow the basic ZFC rules.
That's the punchline.
So within ZFC, CH is independent. You can't prove it true. You can't prove it false. It's just optional.
Optional is one way to put it. Independent is the technical term. Its truth value just isn't determined by the ZFC axioms. That was the aha moment. Cohen essentially showed that the truth of CH depends on which consistent mathematical universe, which model of ZFC you happen to be living in.
That's it, yeah. Mind-bending. It challenges the whole idea of a single, unique mathematical reality.
It absolutely does. Cohen's forcing method is complex, but one way to think about it, as described in some sources like Dana Scott's paper, involves using a kind of generalized truth value.
Not just true or false.
Right. Imagine statements having values from a Boolean algebra, like probabilities. He used models involving random reals. Think of infinitely long sequences of random coin flips.
Okay.
By cleverly constructing these models, he could create situations where, from the inside perspective of the model, you had more real numbers than expected relative to the natural numbers, creating room for those intermediate infinities, making CH false in that specific world.
It's like building realities to suit the outcome you want, but still following the fundamental rules. Incredible.
It truly was a paradigm shift. It showed mathematical truth could be relative to the model.
Okay, so ZFC doesn't decide CH. Gödel's program hoped large cardinals might fix this. How did that pan out? Did these super axioms settle CH?
Well, large cardinal axioms turned out to be incredibly powerful and useful. They helped organize set theory, creating this consistency-strength hierarchy you mentioned.
Ranking theories by power.
Sort of, yes. And for many questions, especially about more concrete things like integers or standard real numbers, theories higher up this hierarchy do tend to agree and give more complete answers. They add a lot of structure.
So they helped in many areas, but the big one, CH.
Here's the twist. The large cardinal axioms we currently know and generally accept, they still don't decide CH.
Still? Why not, if they're so powerful?
Your reason is actually quite profound. CH is what's called not generically absolute. Its truth value can be flipped by relatively small changes to the model, the kind of changes made by Cohen's forcing.
Okay.
But these large cardinal axioms are generally robust against such small forcing changes. If an axiom is true in a model, it tends to stay true in these slightly altered generic extensions.
I see. If the axiom's truth doesn't change, but CH's truth can change in the same process,
then the axiom can't possibly force CH to be either true or false in all those related models. It's insensitive to CH's flip-flopping nature, if you like.
So even our strongest accepted axioms leave CH undecided, which leads us, where? To this multiverse idea. What's that about?
Exactly. Given this persistent independence, some mathematicians started thinking differently. Maybe the goal shouldn't be to find the one true universe V. Maybe reality is this collection of possible ZFC worlds.
The multiverse.
Right. The multiverse language tries to provide a framework to talk about all these different possible set theoretic worlds related by forcing and other methods without privileging any single one. It's about mapping the landscape of mathematical possibilities.
So instead of asking, is CH true, you ask.
You might ask, in which kinds of universes is CH true? Or what properties does the universe need to have for CH to hold? It shifts the focus.
Is it just accepting ambiguity then?
Not necessarily just ambiguity, but maybe diversity. It raises really deep philosophical questions, though, like the ones you mentioned earlier.
Right, the theses, the weak relativist one.
Can we translate everything we talk about in set theory into this multiverse language? Does it capture it all?
Or the strong absolutist.
Is there still some notion of the absolute background universe V that this multiverse picture misses?
And the weak absolutist, perhaps my favorite.
Could there be a special core universe within this multiverse?
Mm-hmm.
A unique, minimal, definable world that serves as a kind of anchor?
That idea of a core is really appealing. Is there any concrete proposal for finding or defining such a core?
This is where we get to the absolute cutting edge. Research by W. Hugh Wooden, proposing something called axiom H.
Axiom H, okay. What does it do?
Well, if axiom H holds, it seems to have some pretty amazing consequences.
Such as?
First, it would imply that, yes, the multiverse does have a core, a uniquely definable minimal world. It would give us that anchor.
Okay, that's big.
Second, it points towards a detailed fine structure theory for this core world, similar to how Gödel's L gave us structure, but potentially much richer.
Deeper understanding.
Third, and this is crucial, its conjecture had hoped to be consistent with all our current, strong, large cardinal axioms. So it wouldn't contradict the powerful framework we already have. It would build on it.
It fits in. And does it say anything about CH?
This is maybe the most startling part. Axiom H, if true and consistent, implies that the continuum hypothesis is true. And not just CH, but many cases of the generalized continuum hypothesis too.
Wow. Hold on. So after this whole journey through independence, multiple worlds forcing CH to be false, this new axiom, this potential core, brings us back and says CH is actually true in that fundamental reality.
That's the potential implication, yes.
Okay.
It's a candidate for a stronger foundation that would settle CH. Not by denying other worlds exist, but by identifying a canonical core world where CH holds. It tries to bridge Gödel's program, find the right axioms with the multiverse view, understand the landscape of possibilities.
It suggests maybe there is a preferred reality among the many possibilities. That's quite something. So from, the limits of what computers can even calculate to these deep, deep questions about affinity and truth. Our dive today really shows that finding mathematical truth isn't just following a straight path.
Not at all. It's this dynamic, unfolding landscape. The meaning of truth, even existence, keeps getting refined, questioned.
Yeah.
Whether it's through these clever constructions like forcing, showing us what's independent, or this grand vision of a multiverse, maybe with a core defined by something like axiom H.
Yeah.
The journey is, well, it's as much philosophical as it is technical.
It really is. It makes you think about the very tools we use to understand the world.
Absolutely. It shows that even in math, the quest for answers pushes the boundaries of what an answer even means.
So here's something to mull over. If even in mathematics, this field we think of as the bedrock of certainty, there are questions that force us to completely rethink what solution or truth even means. What does that suggest about the questions we all grapple with in our own lives and the frameworks, the assumptions we use to try and find answers there?